Okay, so in this lesson, we're going to be looking at another integration technique. In this case, it's integration by substitution. And this, you can kind of think of this as like the integration version of the chain rule when you're deriving functions, because we're going to be doing a substitution with the variable u. So what to look out for with these, I've got a couple of examples, and in both cases of just the normal substitution by integration by substitution, we're going to be looking at two functions of x, sort of like in a product rule scenario where they're multiplying together, or we've got a division. And notably, one of the functions, as in this internal one, is a cubic, and this one's a quadratic. So this is one power higher than this one. You'll see why that becomes important shortly. So the first thing I want to do is replace this function here, 3x cubed minus 7. It's important to get the entire function, not just the 3x cubed. I'm going to let that be equal to u, 3x cubed minus 7. So now what I want to do is I'm going to be focusing on this blue area here for a moment. I'm going to be finding the derivative of this function. So I'm going to be finding the derivative of u with respect to x, and that's going to be 9x squared. Now what I want to be doing is, because I'm going to be substituting u in here, let me just demonstrate this here. I'm going to be having the integral of 6x squared, and this time instead of this function squared, it's just going to be u squared, so u squared. And I don't want to have a dx because I can't integrate a variable u with respect to x. I need to integrate u with respect to u. So in other words, I'm trying to replace this dx with this expression here. So the process goes multiply by dx, divide by 9x squared, and I'm going to get dx by itself is equal to du on 9x squared. So a little bit of switcheroo algebra there. So now I can replace this dx with du over 9x squared, du over 9x squared. And as you can see, I have, because this was one order higher than my quadratic, when I derived it, it turned into a quadratic. And throughout this process, it goes to the denominator. And I'm in a situation, I'm going to stop that looking like a d, that's a 9x squared. I can see that this x squared is going to be able to cancel out with this x squared. So by canceling those out there, I've gotten rid of all of my x variables, and now I only have u variables. So this integration by substitution process involved replacing the higher power with u, and knowing that the smaller power, in this case a quadratic, is going to cancel out with the derivative of this higher power. So now I have 6 on 9, this 6 on 9, which I'm just going to bring right out the front as just a constant. Simplifies to 2 on 3, of course. Then I've just got the integral of u squared du, and that's much nicer. When I simplify this, I get 2 on 3 times, and the integral is u cubed on 3 plus c. And u is that 3x cubed minus 7. So I'm going to have 2. So I'm going to actually do these multiplications in 2 lots of this. So it's going to be 2 lots of 3x cubed minus 7. All of that's cubed. And then on my denominator, I have 3 times 3, which is just going to be 9, and then plus c. So that's as simplified as that one needs to be. And that's a good example of using substitution in order to find an integration result. Okay, so let's find a second example here. And you can see that we've got a different scenario entirely. We have a trigonometric integral here, and it would be very easy for us to look at this and try and do some sort of trig substitution we've done in previous videos with this cos squared x. That doesn't need to happen, however. That doesn't need to happen, however, because we know that cosine derives into sine, and this is one order power higher, so this is going to work nicely. I do want to remind you that cos squared x just means cos of x squared. So just keep that in mind. That's going to be important when we say let u equal cos of x. Now again, we find the derivative of u with respect to x, and that in this case is negative sine of x. And we want to solve for dx, which is going to be du on negative sine of x, which we can now substitute in. So this whole thing is going to be equal to sine of x times by, it used to be cos x all squared, but now it's just going to be u squared. And our dx has turned into du on negative sine x. And this sine x is going to cancel out with this sine x. and I'm going to take the negative value at the bottom of this fraction here and pull it out the front of my integral. And now again, I have u squared du, which we know integrates into u cubed on 3 plus c, and we'll just resubstitute cos of x back in for u. So I get negative cos cubed x all over 3 plus c. So in terms of substitution as an integration technique, you really just need to satisfy one criteria, and that is that the function, you have two functions that are multiplying or dividing, and that one of them will derive into the other one. So up the top here, we had a cubic which derives into a quadratic, and in this case here, we had a cosine function that derives into a sine function. This is important because when you substitute in for dx, it's going to cancel out with the denominator here, so the sine cancels with the sine. And likewise up here, when we substitute in for the dx, our x squared here is going to cancel with this x squared. So one has to be the derivative of the other. Now, there are ways that you can use u substitution when that's not the case. And this is one of those examples. It's called linear substitution. In this case, this function here is not, like, that doesn't derive into this, right? They're kind of the exact same order. So we have to slightly tweak the process of substitution here. I'm still going to look at this, I guess, more challenging function and let that equal u. So I'm going to say let u equal x plus 4. And I still follow the same process. So derive u with respect to x. In this case, it's just 1. If that's the case, then that means that dx equals du, which is nice. That's going to be an easy substitution. But you'll notice what happens here when I put in the substitution. I'm going to get 2 lots of x plus 1. All of that's going to multiply by u to the power of a half, and dx is just du. So I have this, but I don't have anything to cancel this entire function out with. So this is the case where we're going to need to replace our x variable here with u, something in terms of u, because that's what we're trying to integrate with respect to. So we're going to be taking this expression here, u equals x plus 4, and rearranging it so we get x equals u minus 4. What this does, it allows us to substitute into this expression. So instead of 2 lots of x, we're going to have 2 lots of u minus 4, which we will expand and simplify shortly, plus 1, all of that times u to the half du. And now I'm going to do this expansion here. 2 to the u, 2 times u is 2u, of course. And we're going to have 2 times negative 4, which is negative 8, plus 1, which is just negative 7. And then we're having all of that multiply with u to the half. And we're going to distribute now this u to the half to both of these terms. So we're going to have the integral of 2, and remember your index laws from, I don't know, like year 9 or whatever it is, u to the 1 times u to the half. Because they've got the same base, we add the powers here. So 1 plus a half is either 1.5 or 3 halves. So 2u to the 3 on 2. And then we're just going to have minus 7 lots of u to the half du. And we're finally ready to do the integration step. I'm just going to send it up here to do it over here. So we're going to have 2u to the 3 on 2, but we raise the power by 1, so 5 on 2, and we multiply by the inverse, 2 on 5. Now, usually when we do polynomial integration, raise the power, divide by the new power. So dividing by 5 on 2 is the same as timesing by 2 on 5. That's much easier to do. Similarly, we've got minus 7u, and the raised power is 3 on 2. So instead of dividing by 3 on 2, we times by 2 on 3. And we have plus c at the end. And we can finally simplify this down. I'm just going to be multiplying the 2 in, all of it over 5. So we get 4u to the 5 on 2, all on 5, minus, and again, 14u to the 3 on 2 on 3, plus c. And our final step is to resubstitute in for u here with x plus 4. So we're going to get 4 lots of x plus 4 to the 5 on 2, all over 5, minus 14 lots of x plus 4 to the power of 3 on 2, all over 3, plus constant of integration c. So that's an example of linear substitution. And in this case, we have two functions of x multiplying together. And it's very similar to integration by substitution, except we also have to do this linear substitution step in pink in order to get rid of the x variable because it didn't get cancelled out. And one more example of linear substitution here. In this case, we have a function that's squared, but the function itself is the same order or same power as the one on top. So I mentioned earlier that you can do it with division as well. Division is just like multiplication. So I'm going to say let u equal the higher power one, in this case, the more challenging function, which is the squared function, 1 minus 2x. U equals 1 minus 2x. So therefore, the derivative of u with respect to x is negative 2. So dx is equal to du on negative 2. Same steps as before. Again, though, we're going to need to do a linear substitution because we don't have anything down on the denominator that's going to cancel out this 2x plus 1. And so I'm going to have to do my linear substitution step. In this case, I'm going to add 2x, subtract u. So add 2x, subtract u. So I'm going to get 2x equals 1 minus u. And then x is going to be equal to 1 minus u all over 2. Okie dokie. So now we're ready to do our substitution. I'm going to say that's going to equal 2x plus 1. That's going to be 2 lots of, and instead of x, we of course have this expression here. So I'm going to put that in red for color consistency. 1 minus u on 2. That's going to be plus 1. All of that's over u squared du on negative 2. Okay, so I've replaced the x with 1 minus u on 2. I've replaced the 1 minus 2x with u. I should probably keep that color coded. And then I've also got this dx equals du on negative 2 here. Okay, I'm going to tidy this up a little bit. First things first, I'm going to take this negative a half out the front. So I'm going to have equals negative 1/2 the integral of. Now, when I distribute this 2 into this expression, the 2 and the on 2 cancel, and I've just got 1 minus u plus 1. So that's going to be negative u plus 2, right? So I'm going to have negative u plus 2, or 2 minus u if you want. And instead of dividing by u squared here, I'm going to be timesing by u to the negative 2. That's going to be easier in my mind. And then I've got du at the end. Okay, we are nearly ready to integrate. So I'm going to have negative 1/2 times the integral of, and we have to do our distribution, our distributive law. We have negative times a positive, that's going to be negative. We've also got u to the power of 1 times u to the negative 2. Same base, add the powers, 1 plus minus 2, 1 plus negative 2 is going to be negative 1. And then we've got plus 2u to the negative 2 by doing this distribution here, and du. So what I'm going to do now is I'm going to, just to make this clearer, this integration step, I'm going to do two things. First, I'm going to take a negative out of both, so this becomes positive. So I'm going to have positive 1/2. And I'm also going to represent u to the negative 1 as 1 on u. That's going to make it clearer. Make that u a bit nicer. That's going to make it clearer that this expression here is going to integrate into an ln u. We've got our 1 on u, which is just straight off the formula sheet, minus, because I took the negative out, I have to take a negative out of here as well, minus 2u to the negative 2 du. And I'm finally ready to integrate, which I'll do up here. So it's going to equal 1/2 out the front times by ln u. That's that first term. Now this term here, it's going to be negative 2u, and we raise the power, which in this case goes to negative 1. It's very common for people to raise the power to negative 3 because 3 is bigger than 2. But of course, we're in the negative numbers. 1 bigger than negative 2 is negative 1. Try not to make that error. We divide by the new power, and we're going to have plus c at the end. Simplifying it out, we get 1/2 of ln u. I'm distributing in the half now. And in this case, we have a negative over a negative, so it's going to be positive, so plus. And I've also got 1/2 times 2, which is going to cancel out, right? So the 2 here is going to cancel with that 2, and I'm just left with u to the negative 1, which is just 1 on u. I've got my plus c at the end. And the final step is to resubstitute my u expression back in, which is 1 minus 2x. So I get 1/2 of ln 1 minus 2x plus 1 over 1 minus 2x plus c. So that's another example of linear substitution. They can be quite involved, so it's definitely worth your time to practice some of these. For my students, they're in exercise, let me just double check here on my book here. In chapter 11, they're lesson 11D.